All right, welcome back. Want to take a little bit of time here and kind of go over some of the topics that'll be on your upcoming exam. So first off, in 4.9, we talked about definite integrals. Of course, we began first with the antiderivative definition, but then build up to definite integrals. So you can expect that you're going to have some problems where you're going to be dealing with some definite integrals. So, of course, one of the things you could be asked is to reverse any of these derivative rules that you already know. You know the derivative of sine is cosine, so the integral of cosine would be sine. Likewise, integral of sine would be negative cosine. We know that derivative of tangent is secant squared, so of course integral of secant squared would be tangent. We know that the derivative of cosecant is negative cosecant cotangent. So then, of course, the integral would be negative cosecant. And, of course, our power rule that we used that allowed us to do integrals of powers, which is, if it's expressed as a power, add 1 to the exponent to get our new power, and then divide by that power. And, of course, all indefinite integrals have the plus c rule. And, of course, the exception here is -1. Which doesn't work. So 1 over x has its own integral formula that you have to deal with separately. That's actually in the next unit. So, you can expect to have some problems where you're going to be doing some integrals, some indefinite integrals. Please don't forget the constant when you're doing indefinite integrals. And then the other thing that we talked about were what are called differential equations. So you can expect you have a differential equation, usually probably with an initial condition that you're asked to solve. Remember the process, the way to do that is to integrate. And then if we have an initial bit of information, we can use that to figure out the constant of integration by evaluating and working that out. Okay, so indefinite integrals, and then, definite, yeah, I should say indefinite. I'm sorry for the typo there. Indefinite integrals, and then differential equation. I expect to run into at least one of those. We then moved into 5.1, where we introduced working with sums. A lot of the stuff here was kind of building up to later things that we talked about. So where we worked with summation notation, we understood what that was. We developed our sum rules. And so one of the things you can expect is to run into is some problems where you may be given a sum and asked to come up with a formula to express it in terms of n, or even asked to evaluate that formula. As an example of this is from the test for practice. All right, here we have a sum where we're going to want to simplify that sum, right, by distributing through here and then using our sum formulas. And using our sum formulas as we did here. Some of the squares we can rewrite, some of the i's we can rewrite. Do a little bit of simplifying until we get down to a formula. So just like that, you can expect a problem, similar to this on your test. And then here you're actually asked to evaluate it for a particular value of n. We then transitioned to definite integrals, right, using sums. That was in 5.2. Right, so 5.2 is when we got into our definite integrals. Right, so particularly we found the area beneath the curve, right, by setting up a sum, eventually getting our answer, and then taking the limit as we go to n goes to infinity. Right, you'll have a few examples there. Remember, you turned in a couple of examples. We had a few other examples as well. that we did. We kind of defined the formal Riemann sum stuff. And so here's kind of a problem where we're doing the integral by setting up the sum. And so you'll have a problem, and if you go into the practice test, there's actually one there like that. Right, set up a sum to find the area beneath this function on the interval 1 to 6. All right, so here in that particular problem, I'm asking you to write out what would go inside the sum, and then what's the result once we've taken the limit of all that stuff. So here, what goes inside the sum would be this stuff right here, and then we started simplifying and then working out our sums, and eventually we get it down to a limit. So you can expect a question like that as well. The other thing that we talked about in this section with the definition of the definite integral was using geometry. So you can expect some problems very much like problems that we did in the notes, where you're doing a definite integral by graphing it, and then compute, if it's a positive function, computing the area, or as was the case here with this particular one, it was one that was both above and below. So we found the areas above, we found the area below, and we total those two up, and in this case that happened to be 0 for that particular problem. Okay. So using geometry to compute definite integrals. Okay. And then in 5.3 we get into the fundamental theorem of calculus. That's what allows us now to do the integrals by finding the antiderivative. Right, we find the antiderivative, and then we evaluate the antiderivative at those endpoints to get the definite integral. Okay. So as another example, we did integral of sine, which is one we would have been really hard pressed to do with sums, by doing the antiderivative and then evaluating that between 0 and pi. Of course, we found that the area from 0 to pi of sine actually happens to be 2. Okay. And then the other thing we talked about in 5.3 there that you'll want to remember is, so you'll have some problems where you're evaluating some definite integrals. And you're able to do that just by doing antiderivatives. Then we'll have average values. And then we'll have average values, or this result known as the mean value theorem, which basically means, hey, if we take the integral and then divide by the width of the integral, that's the average value of the function. And then if you're asked to find out where does that average value occur, you just set the function equal to the average value and solve that equation. And of course, only pick values that fall in your actual interval. Since we're between 0 and 4, that's why a negative 4 over square root of 3 doesn't count. It's just 4 square root of 3 over 3. As another example, we found the average of cosine between negative pi over 2. So we did the integral of cosine, and when we did that, we got that all of that's equal to 2, and we have to divide by pi. Now here, of course, we didn't ask for where that value occurred at. Where did that average value occur at? But we could solve, it just wouldn't be a very nice answer. All right, when is cosine x equal to 2 over pi? All right, we're going to do the inverse cosine. Here we have the graph, so we get the points there. But basically, you'll be asked about average value, or as we did in this example, not just find out what the average value is, but when does it actually occur? When does the function take on the average value? And then the final thing we talked about was indefinite integrals, doing integrals by substitution, which was the topic of 5.5. So basically, that's reversing the chain rule. So remember what we did is we introduced this new way to write out implicit differentiation that we kind of use as a tool for these problems. And then the process is we recognize a composite function. We recognize what we need to have for du to carry substitution to carry through. Once we make those adjustments, sometimes that involves doing some factoring of stuff or rearranging stuff, multiplying in the inside and outside by the same thing, or in the inside and then dividing on the outside. We can carry the process through. So again, you have multiple examples there of doing integration using that substitution process. And we could, of course, as well have a definite integral where we have to do the substitution first. Remember, you have two options there. You can just ignore the limits, leave them out of the problem, convert it back to your original variable, and then evaluate. Or you can actually change the limits, and then you don't have to change the variable back on a definite integral. Okay. I mentioned to you that we have the just right. Those are the ones where things work out so that we have exactly the variable part we need. We may have to adjust the number to get it to work, as we did here with the 2x. Then we have ones that we can't do right now, where we are missing a variable. We need a variable piece, and we just don't have it. And there's the really hard ones, and you'll probably have one of these. This Papa Bear integral, what I call Papa Bear integral, right? Because it's Goldilocks. You have Baby Bear, you have Mama Bear. We can't do, it's too cold. Papa Bear, we have too much. It's too hot. We have more variable x left over than we need for the substitution. So what we can do there, though, is solve x in terms of u and make that substitution step into our problem. That then gives us an integral in u that we can work out. Often that will require two separate integrals in u, and then we can substitute back in for x. Okay. And here's an example as well of that, where again we had more variable left over than what we needed. More variable left over than what we needed. So we solve for x in terms of u. Solve for x in terms of u. And then we work through that process. Okay, so that's the test. Kind of quick little overview of the kind of questions you can run into. If you do have questions, please ask. Otherwise, have a good day. Good luck.